All right, people, this video is going to introduce the pH scale and walk through some simple pH calculations. And then in the next video, we're going to do more complex pH calculations. All right, so first we have to talk about what happens with water. Remember, I keep telling you that water is like a bunch of piranhas? Well, if piranhas are hungry, they're going to turn on each other. And that is exactly what water molecules do. They self-ionize. Okay, that means that because these molecules are in constant motion, they are going to pull each other apart into the hydronium ion and hydroxide ions. So they are going to transfer that one proton from one to the other and make an H3O plus and an OH minus. And then they bump into another water molecule and then it goes back and forth and back and forth and back and forth. Okay, so this right here is the self-ionization equation for water. Two water molecules come in contact with one another in the liquid phase, and this is in a state of equilibrium to create the hydronium ion and the hydroxide ion, both of which are aqueous, obviously. All right, well, at room temperature, there is about 1 mole of hydronium and 1 mole of hydroxide ions in 10 to the 7th liters, and that's a lot of liters of water. So this happens a little amount. This doesn't happen like a whole bunch, but it happens in equal concentration, so you still get a neutral solution. So the molarity of the hydronium and hydroxide ion concentration is 1 mole per 10 to the 7th liters to give you a molarity of 1 times 10 to the negative 7th molar. Okay, so that's an important value. All right, so when we talk about the measurement of what water is, we always say that water is neutral. It's going to be in the middle because it has the equal amount of acid and it has the equal amount of basic components. All right, and there's also something called the KW, the water dissociation constant. We're going to get into the different KQs in the upcoming chapters, in chapters 16 and 17. But the way that any type of constant is figured out is by taking the concentration of the um, products and dividing by the concentrations of the reactants. And if any of the products or reactants are pure substances like water, you don't count them. So it's really just the concentration of the products. Well, guess what? Here are the concentration of the products, H3O plus and OH minus. And if we plug in 1 times 10 to the negative 7th for each one, we get a KW value of 1 times 10 to the negative 14th molar squared. This is an important number to remember because everything in pH is based out of the value of 14. And this is where we get that number 14 from. Okay, so remember that number. We're going to come back to it. Okay, the pH scale is actually the power of the hydrogen ion, which is why we end up having a little p and a capital H for hydrogen. And it was developed by French scientists, which is why it has, sorry for the bad French accent, pouvoir hydrogenique, and that is the hydrogen power. Okay, how much hydrogen ions, how much hydronium ions we're talking about in your different aqueous solutions. So it is based off of 1 or 0 down to 14. 14 being the max because that is the maximum amount that we can get to with our concentrations, and pure water is here in the middle at a pH of 7. So everything that is going to be lower than 7, including 6.999999 repeating, and 7 is going to be acidic, and 7.00001 repeating O's and above is going to be your basic or your alkaline. substances. Okay, so obviously things like stomach acid and lemon juice and vinegar and all that stuff is going to be acidic, but baking soda, milk of magnesia, which is an antacid, and the antacids that we take is going to be on the opposite end of the scale. Okay, so how do we calculate the pH? How do we calculate the power? Okay, this is all based off of logarithms, and this is something that you have been learning in math class. Don't worry, they're easy. They're logarithms, base 10, okay? But the pH is the negative logarithm of the hydronium ion concentration. It is basically measuring the power, the exponent of your hydronium ion concentration. So star circle highlight this equation right here. pH is the negative log of the hydronium ion concentration. So it is really, really important right now that you go and get your calculators, okay? Push pause on the video and resume play once you have your calculators, because this is probably where kids mess up the most in their calculators because they don't put it in correctly. All right, so go get your calculators, come back. I'll be here. Yay, you're back. Okay, so when it comes to calculating your pH, it is very critical that you put it in the calculator correctly. All right, so you'll see that there is a button, okay, the log button. You want to hit the negative log, and if we're going to calculate for pure water, which is 1 times 10 to the negative 7th, here's another reason why we use the E button. So you're going to type in 1E negative 7 and parentheses and then equal. There are some calculators where you have to put it in opposite. Okay, so it totally depends on your calculator, and I would definitely show you in person if I could, and you can see me in real life to figure it out. But you might have to put in 1e negative 7, then the log, then the negative button in order to get a pH of 7. Okay, so try both ways. It depends on your calculator. I know the TI-84X that I told you guys to get in the beginning of the year does it that way. I am not sure how your cell phones do it. I know that they can't do the next step when we do the anti-log, so make sure that you are looking for that in the right way. Okay, so like I said, okay, pH values. Acidic solutions are going to be less than 7, and neutral is 7 in the middle. Basic solutions are going to be greater than 7. All right, so there is the power of the hydrogen ion. There is also the power of the hydroxide ion. It is much lesser known, but sometimes we need to figure out the pOH in order to get the pH. And the pOH is the exact same thing, the negative logarithm, but this time it is of the concentration of the hydroxide ion. So star circle highlight this equation right here because you're going to use this in tandem with the other one. Okay, so if your solution is NaOH, you're going to see that NaOH is going to give you the concentration of the hydroxide ions. This is a strong base, so 0.01 molar is the concentration of your hydroxide ions, because NaOH breaks up into Na plus and OH minus ions. So this is going to be that concentration. And when you plug it into the calculator, make sure you put it in correctly. Negative calculator, negative log, and then 0.010 equals, and you should get 2. You'll also notice that this value right here is the same as 1 times 10 to the negative 2nd. So really what the log function is doing is it is removing this base 10 and telling you what the exponent is. So the pOH is 2. Well, if the pOH is 2, what's the pH? The pH and the pOH add up to 14. So you can merely take the pH and determine that by taking 14 minus the 2 that you calculated on the other page. And you can get a pH of 12. And then ask yourself, does it make sense? Does it make sense that a base NaOH, that is your Drano, is going to have a pH of 12? Yes, it should. It should be greater than 7. So always look at your substance, see if your substance is an acid or a base. Should you be getting a value when you're calculating these things that is greater than or less than 7? If it's water and you know it's 1 times 10 to the negative 7th, then yes, it's going to be exactly that, 7. All right, so that's the easy ones. Stay tuned for the more complicated ones when we don't have these nice even whole numbers.